Okay, we are looking at section 2.2, polynomial functions of higher degree. And our learning objectives are to use transformations to sketch graphs of polynomial functions, use something called the leading coefficient test to determine the end behavior of graphs of polynomial functions, and to find and use zeros of polynomial functions to help sketch graphs. And if we get to intermediate value theorem, that would just be a bonus. All right, so the graphs of polynomial functions are continuous. That means no holes, gaps, or breaks. Polynomial functions are these nice rounded functions. They have only smooth rounded turns, no sharp turns like like in an absolute value kind of thing where we've got sharp, pointy things. You don't want that. Polynomial functions will only be nice and rounded on their terms. So consider polynomial functions that have only one term, like f of x equaling 3x to the fifth. Graph these on the TI Nspire. Are they the same or different? So if we consider polynomials that have one term only, we actually call those power functions. So I want you to graph x squared and x to the fourth. One more section, 6.3. And you're going to be watching the video for that Friday. That's going to be homework Friday. And I think I'm going to have a little quiz for you to do on Blackboard to make sure you watch the video. All right. Okay, are they similar? You're still working on it? They're pretty close. So the idea is, as I'm launching my calculator, I think what you notice when you're graphing these is that x squared is a little bit more rounded like this, and x to the fourth is steeper here, but a little bit wider on the bottom, something like this. Do you agree with that? Yes. Okay. All right, just something to point out. We still know all about transformations. You guys are expert at transformations now because of your projects, okay? So what kind of transformations are going on here? What do you think, Robert? Left 5? Yep. So this is the parent function, maybe looks something like this, but it's been shifted to the left 5. And what about that negative? Reflected over the x. So I think bottom line is that graph would end up looking something like this. Right? Are we okay with this? All right. Okay, I'm skipping over the. Okay, so at this point, I want to talk about the leading coefficient test, and I have a gift for you, so I'm pausing this lesson so you can work on this gift. Let's see, pausing. Okay, so you have this gift and you have typed in your functions. Can you just tell me for number 1, what did you say? What kind of function? Degree, even, odd, leading coefficient, positive, negative. What do you think, Eric?
The degree is odd.
Okay.
Leading coefficient, positive.
Yeah, positive 1. Okay. And then did the graph start low, end low, high, high? Or?
It starts low and high.
Do people agree with that?
Yes.
Okay. Then what about number 2? Your summary there, Emily?
It's odd degree.
Okay.
Positive leading coefficient.
Okay.
Starts low, ends high.
Okay. And what about number 3? What did you say about that one, David?
Number 3, we got odd degree.
Okay.
Negative leading coefficient.
Negative. Okay.
And it went from high to low.
And it went high to low. Do people agree with that? Okay. For number 4, you got what, Julia?
It was odd degree.
Odd degree.
The leading coefficient was negative.
Okay.
And the graph starts high and ends low.
High and low. All right. How about number 5? What did you say about that one, Jacob?
Degree
degrees even,
Okay,
leading coefficient is positive,
okay,
graph starts high and ends high.
high and high, okay. And how about number 6? Octavia,
The degree is even,
okay,
the leading coefficient is positive,
okay,
the graph starts high and ends high.
okay. And what about number 7? Jackie,
The degree is even,
okay,
the leading coefficient is negative,
okay.
it starts slow and ends slow.
Starts low and ends low. Okay, so hopefully we're seeing some patterns there, so we can answer these follow-up questions here. In a polynomial function, if a polynomial function has an odd degree and a leading coefficient that's positive, it will start what and end what? What do you say about that, Robert?
It will start low and end high.
Do people agree with that? Okay, and we can write that in this way. As x approaches negative infinity, that means the further we go to the left, right? This is as x is approaching negative infinity, means the further we go to the left, right? What's happening to the function? Is it going up to positive infinity or is it going down to negative infinity? Negative infinity. So we're going to say as x approaches negative infinity, f of x approaches negative infinity. Do people agree? Okay, and what about as x approaches positive infinity? Because we know our graph is looking something like this. So as we go further and further to the left, it's going down. So that's why we say as x approaches negative infinity, f of x approaches negative infinity. What about this then? As x approaches positive infinity, f of x is approaching what, Jack?
Positive.
Yeah, so this part here means as we go to the left. This part here means as we go to the right, the function's going up to positive infinity. Are we okay with this? All right, so now what about the next one? If a polynomial function has an odd degree, but the leading coefficient is negative, it's going to start blank and end blank, Frank?
Start high and end low.
All right, start high and end low. And in that way, we can write as x approaches negative infinity, which means as we go further and further to the left, what's the function doing? Is it going up, down? We're talking about a graph that starts high and ends low. So it's starting high and like this. So as we go further and further to the left, what's happening with the function, Kyle?
It's approaching positive infinity.
Okay, as we go to the left, it's going up, up, up. So we're going to say approaching positive infinity. And as x is going to the right, as x approaches positive infinity, what's going on with the function, Kyle?
Approaches negative infinity.
Do people agree with this? Is this okay? This is called the leading coefficient test. It all depends on, first of all, you gotta have a polynomial function, and you gotta analyze what's the degree, is it odd or even, and you gotta analyze what's my leading coefficient, is it positive or negative? Julie? You do need to know the leading coefficient test. Yes, we're kind of summing it up now. All right, what about this next one? If the polynomial function has an even degree and leading coefficient positive, then it does what, Spencer? We're on this one right here. All right, starts high, ends high. Do people agree with that? Yes? And then we can write this in this way. So we're talking about a graph that looks something like this. Starts high, ends high, maybe the graph looks something like this. So as we go to the negative infinity, as we go further and further to the left, what's happening with the function? As we go to positive infinity, what's happening to the function? What are you going to say about that, Pierce?
As x approaches negative infinity, f of x is approaching positive infinity.
Okay. And as x approaches positive infinity, what's happening to the function?
F of x approaches positive infinity.
Do people agree with that? Okay, and then what about if the polynomial function, we're on this one now, has an even degree, but the leading coefficient is negative? It starts blank and ends blank. Tori?
Low and low.
All right, starts low and ends low. And in that case, we're talking about a graph that looks something like this. Maybe it's got a shape that looks something like that. So as we go further and further to the left, what's happening to the function? As we go further and further to the right, what's happening with the function, Max?
Negative infinity, subtracting.
For both?
Yes.
As x approaches negative infinity, the function's heading to negative infinity. And as x approaches positive infinity, the function again is dropping down to negative infinity. Are we okay with this? All right. That's the leading coefficient test. And I'm not going to do this. I want to skip over to, actually, let's just go to the other side of your paper. Okay. Note it says if a polynomial function, in a polynomial function, if a factor occurs twice, the zero is said to have multiplicity 2. That means that the graph will bounce off the x-axis at that x-intercept instead of crossing through. In general, zeros with odd multiplicity will cause the graph to cross through the x-axis. Zeros with even multiplicity will bounce off the x-axis. All right, so let's kind of get a handle on what's going on here. So if I go to a graphs page on my calculator, and I am going to just make up a problem. Let's say 2 times the quantity x plus 4 times the quantity x minus 3. That's my function, right? What are the zeros of this function? David? So -4 is a 0, and 3 is a 0, right? Let's graph it to see that happening. So the graph is crossing through at -4, and it's crossing through at 3. Does that make sense? All right, let's add another graphs page so we can compare this to another one. Let's say, oopsie, let's get a graphs page. So let's try this one. Let's say a -2 times x plus 5, but this time I want to square it, x plus 5 quantity squared. What is going to be the 0 or zeros for this polynomial? Where would you predict this one is going to touch the x-axis? What are the 0 or zeros of this function? Jackie? -5. Okay, so let's take a look at the graph of this. There's -5. Jackie's right, it's touching the x-axis. But how is this graph different than this graph? Well, all right, this one has only 1 0. What else is different about the zeros themselves? What's happening with the, yeah, here the graph is crossing through the x-axis. And in this graph, it's bouncing off the x-axis. Does that make sense? Okay, so that's what this page is about. All right, it's getting you to recognize, is my graph going to cross through at a 0, or is it going to bounce off the x-axis? Does that make sense? So let's take a look at number 1, and let's talk about how to do that one. So we're going to do this one together. Okay, and really, I mean, you can check this with your calculator, but my goal for you is to be able to graph this fairly well without a calculator, okay, using the leading coefficient test that we talked about on the other side of this paper, and what we just talked about as far as will graph cross or bounce at the zeros. So what do I want you to do? First of all, I want you to tell me what's the degree of this. If I was to multiply this all out, we would end up with degree what? 3, right? Because this is x minus 1 to the first, x minus 2 to the first, x plus 4 to the first. Just add up the coefficient, add up the degrees on each of the factors, and you'll get your degree. So this is degree 3. What are the zeros for this function? What are zeros going to be here, Emily?
1, 2, and -4.
Do people agree with that? 1, 2, and -4. All right, so now this is referring to the other side, right? Does it start high and high, start low and low? What is it doing? Spencer?
It should start low and high.
Do people agree with that? Start low and high. Remember, this is an odd degree, and the leading coefficient, I didn't ask you that, but the leading coefficient is positive 1/3. So that means the graph is going to look something like this. Oh, and guess what? You're supposed to put this right here where it says, what's the general shape gonna look like? Just draw that in. It's gonna start low and end high. Everybody with me so far? Okay, at this point, let's actually plot our zeros on the graph. So there's 1, 2, and 1, 2, 3, 4, -4. Does that look accurate? Now, how many times are each of these zeros occurring? Once each, right? 1 occurs as 0 once, 2 occurs once, -4 once. So each of these, each has a multiplicity of 1, right? That means, are we gonna bounce off the x-axis at these zeros or cross through? Cross through. So your task is to take this general shape and get it to go through those zeros. You with me? So we're gonna have it start low, and it's got, oh, you know what I like to do? I like to put like a little, to remind myself, I like to put a little C if they're gonna cross through, and a little B if it's gonna bounce. So I'm just gonna remind myself, cross, cross, cross. So I wanna cross through here, cross through here, cross through here. Does that make sense? Again, we did this all without a calculator. Go ahead and graph this now on your calculator and see if we were fairly close. We want to check for the starting behavior and ending behavior. We want to check to make sure those zeros were correct and that it's bouncing and not close. Does it look okay?
Yeah.
Pretty good? Okay, so let's jump to, you guys probably want to do number 8, maybe, because that looks like the toughest one there. Let's do that one. Sniffing tool. Oh, there is no number 8. You're like, what? I meant number 6. So let's do number 6. All right, for number 6, what do you think is the degree of this, Max?
4.
Do people agree? Degree is 4? I hear yes, I hear no. Emily? 5? All right, why do you think it's 5? Okay, so this is x to the first. This is x minus 2 to the first. This x plus 3 to the second. X minus 4 to the first. You want to add those all up. 1 plus 1 plus 2 plus 1 is 5. This is an odd degree. All right, everybody okay with that? All right, what are our zeros here, Frank?
2, -3, and 4.
2, -3, 4. All right, I got something to tell you. If it's degree 5, spoiler alert, there's going to be 5 zeros. They might be repeated, they might be real, they might be imaginary, as we're going to learn as we go through more of chapter 2, but there's going to be 5. Frank, did you just tell me these?
Yes.
You only gave me 3.
I would say -3 twice.
-3, all right, so let me add that one in twice. So 2, -3, -3, 4. You're still down by 1. Robert? 0 is going to be a 0, right? Because you got to set the x equal to 0, set this equal, right? We're setting each of these equal to 0. So 0 is also a 0. Those are our 5 zeros. Are we okay with this? All right. And what about starting behavior and ending behavior? Pierce?
So, well, okay, so the degree is odd, and the leaves coefficient positive,
Yes.
so that would mean it is going to start low and
there you go.
Are people okay with this?
Yes.
Okay, so our general shape, remember you're drawing this here, just start low and high. Is that right? Something like this? Okay, unfortunately, 1 and 6 both have the same general shape. Oh well, okay, so we're going to plot these zeros. 0, 2, it's not the best grid here. 1, 2, 3, 4. Does that look right? Okay, so your task is to try and get this shape through those points, but can you tell me where should I be putting C's and where should I be putting B's? Where is it crossing through? Where is it bouncing?
It should bounce off at -3 and cross to the S.
So bounce here and cross, cross, cross.
Yeah.
Do people agree with that? Remember, the rule is if it's an even multiplicity, it's going to bounce off the x-axis. If it's an odd multiplicity, it's going to cross through the x-axis. So really, -3, as you can see from right here, -3 has a multiplicity of 2. Whereas this one, and this one all have multiplicity of 1. They're only showing up one time. All right, so go ahead and sketch it. What do you think it's going to look like? So I got to have it start low. It's got to come up here. It's got to bounce, and then it's going to cross, 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 and it's got to end high, right? Start low and high. Does this look okay? All right, does everybody understand what you're doing on this side of the? Yeah. Okay. Okay, one last thing. Zeros of a polynomial function. So a function f of degree n has at most n real zeros, and it's going to have n minus 1, what your book refers to as turning points. So if it's degree 2, for example, you know the graph of a degree 2 is a parabola, right? So it's going to look something like this, right? It's going to have at most 2 real zeros. Well, the graph I just drew has 2 zeros. It's crossing through the x-axis in 2 spots. Is it guaranteed to have 2 zeros? No, because it could have just 1 0, or it could have no zeros. Are you with me? No real zeros. Remember I said, if it's degree 2, you're guaranteed to have 2 zeros. They might be real, they might be imaginary, they might be cheated. All right, we'll take this up after lunch. Our notes here. Okay, so at this point, we were just talking about a function of degree n has at most n real zeros and n minus 1 turning points. And so for our example here, we said if we had a polynomial of degree 2, then it's going to have at most 2 real zeros, at most 2 real zeros. And I just demonstrated that here. This one has 2 real zeros. This one has 1 real zero. That one has no real zeros. All right. And it has at most n minus 1 turning points. This place where it goes from, goes from going down to going up, that would be a turning place. Let's just compare this also to, let me just draw a degree 3 up here. A degree 3 polynomial, as you know from our work earlier, is going to either start low and end high, or start high and end low, correct? Have a shape something like this. So that means it's going to have at most 3 real zeros. The one I just drew right up here has how many real zeros? 3. It's crossing the x-axis in 3 places. If I kind of shift it up maybe a little bit, now how many real zeros does it have? 2. Well, 2 unique ones. This one would be a repeated one, right? Because it's bouncing. Remember, if it bounces, it's 2 or 4 or 6 or 8, even multiplicity. What if I draw it like this? How many real zeros does it have? 1 real zero. What if I draw it like this? How many real zeros does it have? How many?
What?
Still 1, right? You're not getting tricked by that, right? This is going to keep going and going forever, right? It's going to have 1 real 0. How many turning points does this have? 2, because it's changing. Here's a turning point right here. Here's a turning point here. From when it's going up to where it starts going down is a turning point. That's a turning point, and so is this one. All right. Okay, so turning points are also known as relative minima or relative maxima. They're points where the graph changes from increasing to decreasing or vice versa. So finding zeros of polynomial functions is one of the most important topics in algebra. It's closely related to factoring and finding x-intercepts. All right, so real zeros of polynomial functions. If f is a polynomial function and a is a real number, then the following statements are all equivalent. All right, the first one is x equals a is a 0 of function f. All right. And the second statement is x equals a is a solution of the polynomial equation f of x equals 0. Let's get an example going here. Let's say we have a polynomial function like f of x equaling x squared minus 9. We could factor this polynomial into what? Julia? Okay, so it's going to look like what? All right, I can factor that into x plus 3, x minus 3. So x equals what is going to be a 0 of this function? What would be a 0 of the function? If it factors into x plus 3, x minus 3, what must be a 0? 3, right? Or negative 3. Let's just go with 3. So x equals 3 is a 0 of the function, of function f. All right? That's this example right here. But that's equivalent to saying x equals 3, in this case, is a solution of the polynomial equation f of x equals 0. So x equals 3 is a solution of x squared minus 9 equals 0. Very closely related. And that's number 2. All right. What about number 3? X minus a is a factor of the polynomial f of x. So that means I could write this as x minus 3 is a factor of f of x equaling x squared minus 9. And number 4 says a comma 0 is an x-intercept of the graph of the function. So for number 4 here, we can say 3 comma 0 is an x-intercept, I'm abbreviating, of the graph of f of x equaling x squared minus 9. So I just used that example of x equaling x squared minus 9 as, as our working example to show how we could make 3 very closely related statements about the zeros. Are we okay with this? All right. So we don't need to do that. We just did an example like that. Those. Okay, so if you have an example like this, this says find all the real zeros of f of x equaling x cubed minus 12x squared plus 36x. Then determine the number of turning points. So for this, can we factor this polynomial? Any common factors? David? X goes in all these, so we can write this as f of x equaling x times x squared minus 12x plus 36. Can this be factored? Using product sum, does that factor? Remember how this works? Take half of this number and square it. I think this is looking like a perfect square
Yeah.
trinomial, so it's gonna factor into what? X minus
Minus 6 squared.
quantity squared, right? So I could write my function this way. Remember, it's a degree, where is it? It's a degree 3, right? So how many zeros should we have? 3 zeros. They might be real, they might be imaginary, they might be repeated, but there will be 3 of them. Do we know all 3 of our zeros? What are they? 0, positive 6, and positive 6. Are we okay with this? All right, and how many turning points should we have? This graph, remember what we just worked on, 3, 4, 5, 6. It's gonna have zeros at 0 and 6. The general shape is what? Start high, end high, start low, end low. Start low, end high. So I want to fit this shape through these. Do I want to bounce or cross at 0? Cross. Do I want to bounce or cross at bounce? So I'm going to start low, cross through, bounce at 6. Does that make sense?
Yes.
How many turning points do we have? 2. One right here, one down here. Does this look okay?
Yeah.
All right. I think I'm gonna stop it right there, and we're gonna get ready for our ACT quiz. Thanks for watching.
Hi, Dane.
I think